Good morning, everybody. I'm extremely sorry. There is a serious problem with my laptop. I will correct it because I need to clean the laptop and it has got very slow. It is disturbing me. It is creating a lot of problem. But anyway, let us start the lecture. Actually, already 8 minutes have gone. But let us start the lecture now. Let me see. Okay. So yesterday we were designing the Butterworth filters, and I have taken some examples also in which how to design a low pass filter. Designing a low pass filter or designing a filter actually means to find out the order of the filter and the transfer function of the filter. And of course, we want to also know about the poles and zeros of the system, and thereby we can analyze the frequency response. So that's the whole crux of analyzing and designing a DSP system. But today I will start with, because we also know that the strategy to design filters is to create the equations for low pass filter prototype, and from the low pass filter prototype we will use the transformations to get the high pass filter or band pass or band stop filter. So today I will start from the slides in which from the low pass filter prototype, I'm at present talking about the Butterworth filters only.
यहाँ पर हम बोलते हैं x by y. इन दोनों को ट्रांसमिसिबिलिटी कहते हैं.
What was that? I don't know. Something came, but anyway, from the low pass filter prototype, how to design the band pass filter. Okay. Now let us look at what a band pass filter is. By definition, a band pass filter rejects both low and high frequency components and passes a certain band of frequencies somewhere between them, right? Between low and high. So there will be a band that the filter will allow that band to pass through it. All right. Thus, the frequency response Hg omega, that means the magnitude response of a band pass filter, has the following properties. Mod of Hg omega is equal to 0 at both omega equal to 0 and omega equal to infinity. And it is 1 for a frequency band which is centered at omega naught, where omega naught is the mid frequency of the filter, the middle of the band. All right. Now, let us look at what are the specifications of a band pass filter. Omega L is the first passband frequency. Omega U is the second passband frequency. Omega naught is the center frequency of the band pass filter. K1 is the attenuation corresponding to omega L and omega U. K2 is the attenuation for two stop band frequencies. One is at this point. I have not abbreviated this point. I have not given a symbol to this point, but this is the point for, this is the left point of first stop band frequency, and this is the point for the second stop band frequency. So K2 is the stop band attenuation and K1 is the pass band attenuation. What is the bandwidth of the, normally K1, whenever you are finding out the bandwidth of a filter, this will be taken as the 3 dB point or minus 3 dB point. All right, and here at this minus 3 dB point, we define what is the bandwidth of the filter. Bandwidth of the filter will be defined as omega U minus omega L. So this is the bandwidth of the filter. That means the band which can be allowed to pass through the filter, that will be the band that will define the bandwidth of the filter. Now, what is the question now is that what is the transformation which we can use to get the band pass filter from a low pass filter prototype? Now, to convert a unity, what is unity cutoff frequency? That means the filter is normalized filter. To convert unity cutoff low pass filter whose transfer function is given as Hs. Now we have to convert it into a band pass filter Hs. with lower cutoff frequency omega L and upper cutoff frequency omega U. All right. What we will do is we will replace S, this S. What is this S? This S will be there in the transfer function of the low pass filter prototype. Every S in low pass filter prototype will be replaced with this term, S square plus omega L into omega U divided by S omega U minus omega L. If you replace every S in the transfer function of the low pass filter prototype, the resultant transfer function that you will get will be of the band pass filter. And for a band stop filter, this omega U minus omega L will come on the top, and this term will, the denominator term will come as numerator and numerator term will come as the denominator. Only that is the difference. So in a to convert it into a band reject filter or band stop filter, what you have to do is you have to replace every S in the low pass filter prototype with this term, right? So these are known as the transformation. These are analog transformation. Actually what we are doing is we are converting an analog low pass filter prototype to its analog counterparts as high pass filter or band pass filter or band stop filter. Using the strategy, I hope is clear now. We will design for the low pass filter prototype and we will apply the transformations to get either a high pass, band pass or a band reject filter. Correct? These are the specifications of a band stop filter. K1, K2 are the two attenuations, and this is the same as I have already explained. These are the corresponding frequencies for band stop filter. Band stop is actually where you block a certain band of frequencies. Not rest of the frequencies will be passed, but certain band will not be allowed to pass through it. So this figure actually explains the crux of the summary of what we have discussed as far as the transformations are concerned. These are analog to analog transformation. This is the first figure is the Butterworth prototype response, where 20 log Hg omega is expressed in terms of dB. This is the unity cutoff frequency. That means it is a normalized low pass filter prototype response. Clear? If we want to get a low pass filter with omega C as the cutoff frequency, then every S, this is the transformation. Every S in the low pass filter prototype transfer function will be replaced with S by omega C. You will get this filter. If you replace S with omega C by S, you will get this high pass filter. All right. If you replace S with S square plus omega U omega L S into omega U minus omega L, you will get a band pass filter. And this way, and using this transformation, you will get a band stop. So this slide actually gives us the summary of the transformation that can be applied to get the resultant transfer function for different types of filters. Okay. Now, this was the theory for analog filter design. This was the explanation of what is a Butterworth filter, what is the equation of Butterworth filter, how to design Butterworth filter in the analog or the continuous domain. But now we will study the techniques of IIR filter design, IIR digital filter design. Okay, there are basically three techniques of IIR digital filter design. The first technique is approximation of derivatives. The second technique is impulse invariant method, and the third very popular technique is bilinear transformation. So one by one, I will complete with the digital IIR filter design also. So let us look at I will start with IIR filter design, approximation of derivatives. Okay. Now let us look at what is the approximation of derivatives technique. So we have to design the IIR filters. IIR filter design techniques depend mainly on converting analog. So you can certainly ask a question that why, when the subject is DSP, why we studied analog filters, right? Why we went into the details of the S domain when we have to deal with the Z plane, why we entered into the era of S plane. Now that's what is the meaning of this line. IIR filter design techniques depend mainly on converting existing analog filters to a digital one. All right, analog filter can be described by three methods: by writing its transfer function or system function in this form, or by defining its impulse response, which is related to the system function. So HAT is the impulse response with the system function, that is the relationship. So we can express the analog filter in this form, in the form HAS also, right? And or by, we can also describe the analog filter in terms of differential equation, linear constant coefficient differential equation. Each of these three, so these three methods are there by which we can represent, by which we can describe analog filters. Now, each of these three characterizations lead to alternative method for converting the analog filter to its digital equivalent. Okay. Now, the system function HAS, what is HAS? Is the transfer function or the system function for analog filter. The system function HAS is stable if all its poles lie in the left half of the S plane. Hence, the conversion is effective if the j omega axis. What is this j omega axis? What is in the S plane? The x-axis in the S plane is sigma. The y-axis is j omega, j capital omega. Sigma is responsible for the transients in the system, to study about the transient behavior of the system. J omega axis in the S plane. How do we convert from S plane to the Z plane? We take this J omega axis, we join the endpoints of the J omega axis to form a circle that we call as the unit circle. That means the J omega axis in the S plane map into the unit circle in the Z plane. Everything on the left of the J omega axis will come inside the unit circle, and everything on the right side of the J omega axis will go outside the unit circle. So there is a complete analogy between the poles lying on the left half of the S plane, going into the going inside the unit circle, and poles lying outside, poles lying on the right side of the j omega axis, going outside the unit circle. Right, the left half plane of the S plane map into the inside of the unit circle. That is stable. This is important because if the analog filters are stable, they will lead to a stable digital filter. Okay, so let's look at this method of approximation of derivatives. We'll use the differential equation. I explained you there are three methods to put up the analog filter. The one is system function, impulse response, or the system function in terms of HAS put in terms of impulse response, and the third method is the differential equation. Approximation of derivatives will use the differential equation method. What we will do is we will convert the differential equation into difference equation. Okay. So let us consider a first derivative dy by dt, and because we have to go to now this small t is there in the analog domain. We know that if we have to go to the digital domain, what you have to do is basically replace this small t with n capital T. That's what is sampling. That's what sampling is. So what we will do is dy by dt, and we replace this t with nt. And this approximation is known as backward Euler's approximation. We can write a derivative as y of nt minus ynt minus t. That means the difference of one sample time, right? Difference of one sample divided by one sample time. So that's what is known as the backward Euler's backward Euler approximation. Backward approximation, excuse me, where the derivative can be expressed like this. Sorry. Now, this y and t we can always write as yn, because for simplicity we can write, we know that yn is actually y of n capital T, but we can write it like this, yn minus 1 divided by t, right? And if we take the z transform of this, taking the z transform of this will be 1 minus taking the z transform and getting the transfer function. This will be yn minus 1 by t will be equal, or for corresponding to yn it will be 1, corresponding to yn minus 1 it will be z to the power minus 1, because there is a delay of one element, and divided by t. So this hz will be equal to the system function from yn. What we will get is hz, and hz will be equal to 1 minus z to the power minus 1 divided by t. If we pass yn from this transfer function, what is the meaning of this diagram? If we pass yn from this filter with the transfer function 1 minus z to the power minus 1 divided by t, we will get yn minus 1 by t. And in the analog domain, if we pass yt from a transfer function with s as the transfer function, you will get dy by dt, right? So in analog domain, s is equal to, in analog domain, this s factor in analog domain is actually equal to 1 minus z to the power minus 1 by t in the digital domain. So that is the transformation that we get. So we can write it like this. For the analog derivative, the system function is given by hs is equal to s. If you analyze, it will be equal to the derivative of the y, right? hs is equal to s, whereas the digital system function is 1 minus z to the power minus 1 divided by capital T, which leads to, so we have to establish the equivalence between the analog and the digital equivalent, digital parts. So s is equivalent to 1 minus z to the power minus 1 divided by t. So this is the transformation that we will use to convert a first derivative in the differential equation into its digital equivalent. Okay. And let us now look at the second derivative, how the second derivative will behave. So it is d2y by dt square. So this is equal to d by dt of dy t by dt, and dy by dt we know it is what is dy by dt? Dy by dt we know it is yn minus 1 by t. So you have to take the double derivative here. Double derivative of, once you take the double derivative and apply the double derivative formula, you will get yn minus 2 yn minus 1 plus yn minus 2 divided by t square. So therefore, in frequency domain, what is the digital equivalent of, what is the analog transfer function in this case? It will be s square. For the second derivative, it will be s square. And what is the digital equivalent of this? If you take the z transform, this will correspond to 1. This will correspond to minus 2 z to the power minus 1, and this will correspond to z to the power minus 2 divided by t square, right? If you pass yn from a system having this transfer function, you will get this equation. That's what is the meaning. So s square in analog domain is equivalent to 1 minus 2 z to the power minus 1 plus z to the power minus 2 divided by t square, and we can write it 1 minus z to the power minus 1 divided by t whole square. So this equation is for the first derivative. S is equal to 1 minus z to the power minus 1 divided by t. Now if you look at the second derivative, it is 1 minus z to the power minus 1 divided by t whole square, and in analog domain it is equivalent to s square. It is s equal to this. For second derivative, s square is equal to 1 minus z to the power minus 1 divided by t whole square. And in general case, for the kth derivative, it is equivalent to Sk equal to 1 minus z to the power minus 1 divided by d whole raised to the power k. This is for the kth derivative, right? So what we are doing is we are approximating the derivatives in the differential equations to convert an analog filter to a digital filter. So any s in the transfer function, when we are converting into digital function, will be s will be replaced with this 1 minus z to the power minus 1 divided by t. S square will be replaced with this factor, and any other derivative will be replaced, giving the value k. Value of k will be replaced with this factor. Okay. Now the system function for IIR filters is obtained as a result of approximation of derivatives. Now, how do we obtain the system function? In the digital domain, Hz will be equal to Hes. This will be given. We know, because we already know what is the transfer function, what is the system function in the analog domain. That's what the procedure I was telling you. The procedure is to have all the transfer functions which are already existing corresponding to analog filters. Once we get Hes, you replace every s with 1 minus z to the power minus 1 divided by t. So once you do that, you will get the digital filter out of that. This is the method of approximation of derivatives. Now let us investigate the implication of the mapping from this s plane to the z plane. Now here it is s is equal to 1 minus z to the power minus 1 divided by capital T. If I calculate z from this equation, z equal to 1 over 1 minus st. Right. Now, if I replace s with j omega, because I assume sigma equal to 0, I am only concerned about the imaginary axis points on the imaginary axis, then the j omega axis is mapped into z equal to 1 over 1 minus j capital omega capital T. S is replaced with j omega. And I can divide and multiply by 1 plus j capital omega t, and I will get this formula. And if you analyze, if you put the values of sigma, omega, so this is the, let me, okay. The y-axis in the S plane is mapped. What happens with the approximation of derivatives is that when I say that the j omega axis will be mapped into inside the unit circle, that will come afterwards. But what happens with this mapping when we replace s with 1 minus z to the power minus 1 capital T, and we reach here, and if we, this is the j omega axis, this is the left of the S plane. Every point on the left of the S plane will be mapped through this circle. For this equation, when the mapping is done with s equal to 1 minus z to the power minus 1 divided by capital T, right? Any point in the left hand plane will be mapped to points inside that circle. What is this circle? The y-axis in the S plane is mapped into a circle of radius half. The radius of this circle is half, with center at z equal to 1 by 2. So this is the center. Everything with the method of approximation of derivatives, everything on the left hand side of the j omega axis will be mapped into this circle. If we use this method where s equal to 1 minus z to the power minus 1 divided by t, all right, we can improve upon this. Now, the possible locations of the poles of the digital filter, once we get the digital filter, because when we enter into the Z domain, it will be digital filter. How did we enter? We replaced every S with 1 minus Z to the power minus 1 divided by capital T. The possible locations of the poles of the digital filter are confined. What is the problem with this method? So the poles are confined to very low frequencies in this method of approximation of derivatives. As a consequence, the mapping is restricted to low pass and band pass filters with a relatively small. It is restricted to low pass filters and band pass filters with very less, with very small resonant frequency. It is not possible to transform a high pass analog filter. With the problem with this type of transformation, what type of transformation? Z equal, S equal to 1 minus Z to the power minus 1 capital divided by capital T, because the circle is inside the unit circle. Everything is confined into a very small circle. That means it is leading to very low frequencies. All right. So it is not possible to transform a high pass analog filter into a corresponding high pass digital filter. Now, in attempt to overcome these limitations, more complex substitutions for the derivatives have been proposed, such as, now more complex, because for the first derivative we used this approximation. For the second derivative, we use this approximation. But what happens with this type of approximation? The mapping is into this type of unit, this type of circle, where the center is 1 by 2 and the radius of the circle is only half. That means the circle is there, and that means the implementation will be confined to very low frequency. Now, we can improve upon this situation by little more complex substitutions, where dy by dt is equal to 1 over t sigma alpha k, and we replace with this type of substitution. And this will lead to what will be the mapping. Using the same method, the mapping will be every s will be replaced with 1 over capital T, k going from 0 to capital L, alpha k z to the power k minus z to the power minus. So this is the, if we use this kind of mapping of from S to Z, then when Z is equal to j omega, S is equal to, we can find out that X is. In this case, which is pure, which means by carefully selecting alpha k and S, if we carefully select alpha k, this alpha k and S, then j omega axis can be transformed into the unitary circle. This can be done by using optimization. So this is a little complex method that we can achieve the mapping of the left side of the S plane into a unit circle, right, by using this approximation. But this will become a little complex. But if we use this kind of mapping, right, then in that case, this is the mapping. That means every point in the left hand side of the S plane will be mapped to this circle with the radius 1 by 2. Now let us look at some examples now. This example I think is there in your due sheet also. So let us look at this example. What we have to do is we have to convert the analog band pass filter. This is the transfer function given for analog band pass filter with system function. Now HAS is given to be 1 over S plus 0.1 whole square plus 9. Okay. And we have to convert it into a digital filter. What is the transformation? I said that if you use this transformation, every S is to be replaced with 1 minus Z to the power minus 1 divided by capital T. From where this mapping has come? This mapping has come from approximating the derivatives. So we use this backward Euler approximation, and we got this transformation, this mapping, right? So let us replace every S in the system function of the analog filter with 1 minus Z to the power minus 1 divided by capital T. This is the method of approximation of derivative. So HAS will be converted into HZ once we replace S with this factor 1 minus Z to the power minus 1 divided by T. And we solve it further, right? HZ will be equal to this will correspond to some constant value, because the Butterworth filters, in the case of analog Butterworth filters, we will have only poles, right? So T square, this is a constant factor. This denominator polynomial is a second order denominator polynomial. If you look at 1 minus Z to the power minus 1 plus Z to the power minus 2, these are coefficients. 2 into 1 plus 0.1 t, and all these are coefficients for the z to the power minus 1 factor, and this is the coefficient for z to the power minus 2. And choosing a value of t equal to 0.1, right? T should be, and by adjusting the value of t should be less than or equal to 0.1 for poles to be in near the unity circle. Then if we choose t equal to 0.1, we will get the pole, because the poles will, this is a second order transfer function, and you know that whenever there is a second order transfer function, this is a second order transfer function, right? And you know that the two complex poles will be there, so these will be the pole positions. P1.1 and 2 will be equal to 0.991 plus minus j 0.27, and in the polar form it will be 0.949 e to the power plus minus j 16.5 degrees, right? So these will be the two pole positions from this. So what we have done, actually, we started with the with the system function of the analog filter. We used this transformation of approximation of derivatives, and we replaced s with this factor, and we obtained the digital filter. We obtained the transfer function of the digital filter, and we also obtained the poles. But I have already explained you the problem with this approximation, 1 minus z to the power minus 1 divided by t. What will happen? All the points on the left hand side of the j omega axis will be mapped to this circle with radius half and center point at half, z equal to half. And this type of approximation can be used for lower frequencies or band pass filters with smaller resonant frequencies. But in the case of high pass filter, this may not be a very suitable option using the approximation of derivatives, right? So this is the procedure of getting the digital filter from the analog filter using the approximation of derivatives. Let us look at one more example. Convert the analog band pass filter in the previous example. So in the previous example, we firstly we use 1 minus z to the power minus 1 divided by capital T. This approximation, if you remember, this is the approximation we use, right? First order derivative approximation. But the problem I explained with this diagram. But I further said that we can improve upon this situation if we use this approximation. If we use, in attempt to overcome this limitation, more complex substitutions for the derivatives have been proposed by scientists. So if we solve this approximation of derivatives, then we will reach to this approximation. So s is equal to 1 by t alpha k z to the power k minus. So if we use this approximation where k is selected to be 1, where k is also 1 and alpha k is also selected to be 1, and in that case if we use this approximation, right, s equal to 1 by t z minus z to the power minus 1, if we use this approximation and we replace every s in this transfer function with this substitution, right, we will get this transfer function. Now what happens? Now what happens is this system using this 1 minus z to the power minus 1 divided by capital T, it was having two poles, right? When we converted from the analog domain to the digital domain, the number of poles remain the same. But when we use this approximation, we got this transfer function, and if you see carefully, it has got the denominator polynomial is of order 4. That means it has 4 poles, while HS has 2 poles, right? The analog filter has 2 poles, which means that the conversion has led to more complex systems. If you remember here, I said in attempt to overcome the limitation, what was the limitation? This was the limitation. Now, in order to overcome this limitation, more complex substitutions are proposed. What is the substitution? This is the substitution, right? And we used the first factor, the first term of the more complex substitution, and we saw that the system, the digital filter resulted has 4 poles now. When it has got 4 poles, that means the complexity of the system has increased. HZ has 4 poles, while HS, what is HS? This is HS. HS has got 2 poles, HZ has got 4 poles, which means that the conversion has led to more complexity. All right. So in transforming an analog filter to digital filter, we must obtain either HZ from the analog filter design. In such transformation, we generally require that the essential properties of the analog frequency response be preserved in the frequency response of the resulting digital filter. This implies that we want the imaginary axis of the S-plane to map into the unit circle of the Z-plane. The second condition is that a stable analog filter should be transformed to a stable digital filter. That is, if the analog system has 2 poles only in the left half S-plane, then the digital filter must have poles inside the unit circle. No problem if the system gets complex, but at least the poles must lie inside the unit circle. Then only the system will lead to a perfect conversion. You know, IIR filter design, if you remember the comparison that I was showing between the FIR filters and IIR filters, for given specifications, FIR filters will always be taking high order. Let us say if you are given some specification, and if you choose FIR strategy to implement those specifications, you may require the order of the filter to be 40. I'm giving an example. But if you use an IIR design strategy to design a filter with the same set of specification, IIR filter may require an order of, let us say, 10. So that is the difference between the implementation of the filters either through the FIR strategy or IIR strategy. But FIR filters are always stable, right? Because there are no poles. When there are no poles, nothing will go outside the unit circle. So they are always stable. They will always give linear phase. Whereas IIR filters are very prone to instability because poles are there. Once, due to any reason, if the poles move outside the unit circle, the system can become stable. So with very careful, by applying very careful design strategy, you can keep the poles inside the unit circle, and that will lead to a stable digital filter design. All right. So what I will do is I will finish my lecture here. So I have completed with the approximation of derivatives method, but I will in my next lecture I will discuss about the impulse invariant method, very important methods, these two, which will actually define the analog domain and the digital domain, and how the analog frequency is related to digital frequency, and how you can convert the analog filters to digital filters perfectly, right? So 2 methods are there, impulse invariant method, and the second method is bilinear transformation, that I will cover in my next lecture. So, but I have already covered the IIR filter design using the approximation of derivatives, right? So I think this question is there in your due sheet also, and there are more questions. If you find any problem, you can always ask, right? Anyway, thank you so much. I finished my lecture, and I apologize for late joining because of my system issues. But anyway, thank you so much for joining.